So again, welcome back to our latest lecture session. So again, let's have a quick review of what we have been up to in the last lecture session. So I guess right now, or in we are now at the fag end of the course, right? So we, I guess, need to be able to take a holistic approach to be able to understand, let's say, quantitatively and qualitatively any system that we look at, right? And in that context, to be able to visualize that, we looked at a particular set of examples, I believe, over the last 3 sessions, right? So let's just quickly summarize them. So in the first set, we looked at one particular case where we looked at no other reactions, right? Except redox, obviously, except the redox, right? And we calculated the P values for 2 half reactions, right? Except the redox. Right, and I think in this scenario we saw that I think PE1 was greater than PE2, right? And from this you can then know that, let's say, half reaction 1 will go as written or as reduction, right? And the second half reaction would need to proceed as oxidation, right? But when we looked at, what do we say, the example with respect to the iron half reaction and considered complexes, right? Considered the formation of complexes in conjunction with the redox process, right? As in, I believe we have this particular half reaction, right? Fe3 plus electron goes to Fe2 plus. This was our first half reaction, right? So when we calculate this particular P value, right? So that's equal to P naught, right? Minus 1 by n, 1 electron transfer, right? Into log activity of Fe2 plus, right, by Fe3 plus, right. This is from our understanding of the relevant system. So when we looked at the particular case, when we considered that no complexes would be formed and we would only have the redox reaction going through, right, or the redox process involved, we saw that the PE1 for this half reaction was greater than the PE2 of the other reaction that we considered, right. But with our knowledge or the background that we had, let's say we know that we need to consider complexes in this case, because here you have, what do we say, electron poor compounds here, right. Again, we have complexes here that can be formed, right, both with respect to or with Fe2 plus and the Fe3 plus cations, right. So when we looked at that and then recalculated that, though, we saw that Pe1 was actually less than Pe2, right. So what does that mean? 1 would proceed as oxidation, right, and 2, the second half reaction would proceed as reduction or as written, right. And again, what does this mean now? What does this change mean? That now Fe2 plus will act as the reducing agent and reduce the other relevant compound, right, and reduce the target, let's say. Let me leave that there, I guess. Yes. This was the other scenario we looked at, but let's say the final scenario that we looked at, let's say, that approached what you would expect out there in the system was, we considered the formation of a solid or precipitation too, right. So obviously out there in the nature you would have precipitation, you would have complex formation and redox process all occurring simultaneously, and obviously the relevant acid base reactions too. So when we calculated that for that particular scenario or analyzed that particular scenario, right, we had, what do we say now, precipitation, we looked at or considered complexes, right, and obviously in conjunction with the redox process. We saw that P1 was far less than P2, right, indicating that for those conditions Fe2 plus is a strong reducing agent, right. So I guess hopefully this approach, right, or these sets of examples should have helped illustrate what we have been trying to understand since the last couple of months, I guess, right. So as in all these chemical processes that we have discussed thus far, the acid base, complex formation, redox, right, precipitation, they go hand in hand and are interlinked, right. So it's a fine balance between all these processes, obviously at equilibrium, right. So we looked at these aspects, right, and now we are going to move on to what do we say, the EH approach, right. Until now we looked at understanding the relevant redox process from the context of PE, right, which is minus log activity of the electron, right, and understood the relevant aspects or analyzed the relevant aspects. But in general too, people, or you might have heard about the electrochemical cells, or in general, I guess you might have heard of me referring to PE as or the P naught values as redox potentials. Well, that's slightly erroneous though. When we say redox potential, it's actually EH values that we are talking about, right? Again, electrochemical cells, these are relevant to the electrochemical cells, right? So we are going to discuss these aspects though, right? Again, before we go further though, right, again, similar to what we have done thus far with each of the process, we'll also briefly look at, let's say, how to set up these, what do we say, equations to be able to solve for the system at equilibrium, right, by hand now. Again, we are going to have a very brief outlook again, and the reason being that, as you know, in redox process, mostly it's the kinetic aspects that are relevant. These aspects that we are analyzing, P, and such, or using the Wiemann-Tech to be able to understand the system, will only tell you what you would expect, let's say, if equilibrium is reached, right? What are the conditions prevailing, let's say reducing conditions or oxidizing conditions or such that would prevail if equilibrium is reached, right? But again, keep as we know, right, the kinetics play a huge role, and we should be careful when looking at analyzing the system, just looking at the PE values, right? For example, in this particular case, or the example where we looked at, just because we say that Fe2 plus is a strong reducing agent and will reduce the other compound doesn't mean that it can go through, right? Because the kinetics can be relatively slow, right? But at least you will be able to understand which compound would act as a reducing agent, and thus which compound would be reduced, and thus and so on, right? At least that will help you understand the system. Yes. So again, we are going to have a very brief outlook, right, with respect to how to solve it. So I guess the general approach, how have we solved all these equilibrium problems now, right? The general approach, what was that now, right? How have we solved the equilibrium relevant aspects now, right? We always looked at our components balance model, right? So similarly too, here we can follow the component balance. So let's say if I'm looking at this particular set of example though, so what can the possible components be, right? So you usually would have chosen Fe3 plus and Fe2 plus though, right? But how would you account for these redox reactions though, right? So in such a case, right, you will choose your electron as one of the components too, right? But you will consider that obviously, let's say the relevant concentrations of these electrons are relatively low, right, or negligible. But choosing these electrons as one of your what do we say components, let's say, will help analyze the or calculate the system, I guess, right, or it will help in getting at the system. But obviously again, then you need to what do we say look at manipulating the other two components too, right? And how does Wiemann-Tech calculate this? Again, with respect to Wiemann-Tech, right, what is this software about, or what will this help give me an understanding about? Again, keep in mind that Wiemann-Tech doesn't give you any idea about how fast or slow the reactions are. Wiemann-Tech is software that we can use to understand what the system would be if and only if the system reaches equilibrium, right? So when you try to use Wiemann-Tech or utilize Wiemann-Tech to analyze this redox what do you say process, right, or redox reactions, that's something to keep in mind, that you are only understanding the systems that would, or the conditions that would prevail at equilibrium. But again, that the kinetics play a huge role, so that's something you need to be able to calculate looking at the relevant rate constants or such, right? So Wiemann-Tech though, again, I guess the aspects here are, obviously it will choose Fe3 plus, Fe2 plus, and what do we say, electron as components, right? But I guess something that I haven't mentioned out here, the issue is that if this is written as it is, right, with such formation equations, right, you see you can form one of your components from the other two components, which hits at one of the fundamental, what do we say, aspects of our what do we say now, our component balance equations, right? So how does Wiemann-Tech go about this now, right? To be able to get out of this particular, what do you say, quandary, I guess, Wiemann-Tech introduces a dummy variable, right? Fe3 plus by Fe2 plus, x is your dummy variable, right? And it now, let's say, uses this as a particular what do we say way to be able to help then solve the relevant aspects. As in, let's say, what will your total electron balance be? It's going to be equal to, let's say, x, or the Fe3 plus, Fe2 plus, right? And if there are other target compounds, let's say arsenic 5 to arsenic 3 for the relevant half reaction, plus so on and so forth. So how will this electron transfer or the total electron balance work now? So let's say if the electrons are being donated from this particular half reaction to this particular half reaction, right? So then this particular term will be positive and this will be negative and so on, right? And again, why is that? Because the electrons are being, what do we say, or Fe2 plus, let's say, is acting as a reducing agent in this case, right? So then that's donating the electron. So X in this case would be, or the dummy variable here with respect to the balance of the electron would be positive here, and the one with respect to the arsenic which receives, let's say, and this is oxidation state 5 for arsenic, if that's not clear, would be negative here, right? And thus it would help understand or analyze the system. So similarly again, if I am writing Fe2 plus total balance, it would be Fe2 plus relevant components, not component species with respect to the complexes, right? And also let's say X Fe3 plus by Fe2 plus, right? And so on, right? So again, with respect to Fe3 plus 2, it will be, I guess, the negative there, right? And so thus, Vimentech helps or tries to what do we say, arrive at the solution, right? So again, such a brief outlook is good enough for us, right? So once you understand the approach, you can get that done if necessary, but obviously Vimentech will cut down on the time. So now we are going to move on to the next aspect that we have talked about, which is the EH approach, right? Until now we have looked at the PE approach to understand the system and the relevant aspects. But again, in environmental process or such, you might have looked at people looking at electrochemical cells or such for promoting or propagating certain kinds of reactions or such, or utilizing the relevant transfer of electrons in a worthwhile manner, I guess, right? So in that context, I guess, right, EH approach is worthwhile because it helps understand the system in a better manner, right? Or the electric potential here, let's see. So let's see what this is about. But before we go further, we need to understand a few aspects here. Again, keep in mind that everything boils down to one particular, as in, let's say, one particular aspect. As in, every system, let's say, or every process would be driven by the sole motive of decreasing its energy, or the energy of the system would want to be decreased now. And this is something we looked at in our initial classes, right? When we looked at, I guess, the Gibbs energy of the system, right? Or Gibbs energy of the mixture, right? You saw that it is always driven towards, being at its lowest possible state or value, right? So again, keep that in mind when we work out these aspects. So just to, what do we say, refresh your memory, if you remember this, we had delta G naught, right, was equal to, what do we say, minus RT natural logarithm of K. K here is the equilibrium constant, obviously, right? So I'm just trying to illustrate an approach where we are going to be able to try to link, let's say, this Gibbs energy of the system, let's say, with the PE value or molar Gibbs energy of the electron, let's say, to be more specific at standard conditions to the PE value, right? Let's see how we can arrive at that particular aspect. So if people can refresh their memory, we looked at this fundamental, what do we say, equation earlier on, let's say, or very early in the what do we say, class, right? And let's consider this particular, what do we say, half reaction, let's say, right? Plus electron goes to half H2, right? This is going to be gas, and this is in general the reference, what do we say, half reaction, right? So the equilibrium constant for this would be, let's say, equal to 1, let's say. And now how do I calculate the molar Gibbs energy of this particular, what do we say, electron here, right? At standard conditions again. Molar or standard molar Gibbs energy of this particular electron, how can I calculate that now, right? So if people remember that, right, this was based upon your particular, what do we say, analysis, as in the delta G of the reaction at the standard conditions was equal to the stoichiometric coefficient, right, times the chemical potential, right, of the products summation minus that of the reactants, right? And again, chemical potential was nothing but also equal to the molar Gibbs energy of that particular element or compound, molar Gibbs energy of formation if required, right? So how do we apply this to this particular equation now? Here it's going to be half times Gibbs formation, let's say, standard condition H2, right, hydrogen in the gaseous state, minus that of, let's say, what do we have here of that of H plus, right, minus that of the electron. Again 1 is the stoichiometric coefficient here, right, but again these are the elements here, let us say, right, and thus these two values would be equal to 0, right, and here we know delta G of this particular reaction was equal to minus RT natural logarithm of K, right, and the equilibrium constant for this is set as 1, this is the reference half reaction, right. So, this value would also be equal to 0 now, right. So, now what do we have here though, I guess that G naught is equal to 0, right. So, again taking this further, right, similar to our mu I at non-standard conditions equal to mu I naught, right, plus RT natural logarithm into activity of that particular compound. This is another particular what do we say equation that we analyzed when we looked at trying to calculate the chemical potential of the system at non-standard conditions, right, when the activity was no more equal to 1. So, that is the case that we have here. So, if I apply this out here, let us say, so the molar Gibbs energy of the, let us say, the particular electron, but no more at the standard condition, will be equal to that at the standard condition plus RT natural logarithm of activity of the electron, right. So, as we just looked at, this particular value is equal to 0. So, now I can simplify my system, right, and write this particular molar Gibbs energy of the electron to be minus 2.303, right, RT times PE, right, and simplifying this further, let us say, looks like it can be written as minus 5.71 kilojoules per mole times PE, right. Again, I know we are just illustrating these what do we say derivations here, but just try to understand the system here, right. So, here what we have what we are finally up to, or what the take home message here is that I can relate PE, which is gives me a measure of the activity of the electron, to the molar Gibbs energy of the electron here, right. So, that will then again help me understand, let us say, if let us say a particular electron, a molar Gibbs energy of a particular electron is at a higher state, let us say higher energy state. So, I guess how would the reactions proceed now? The reactions would proceed in such a way that the energy would decrease, right. So, keep this in mind when we try to understand the relevant system later. So, here in such a manner, right, we can relate the molar Gibbs energy of this particular electron, let us say in particular system, with respect to the PE of that particular half reaction, right. So, let us move on, let us say. Before we go further, I guess there is one other aspect that I need to write up here. So, another approach that we need to also consider obviously is the EH approach. So, again here we people might be familiar with this concept of PE, right, or the molar electrical energy, right, and that is going to be equal to the product of the charge, electric potential and Faraday's constant, right. Molar electrical energy, charge, electric potential and Faraday's constant, right. So, it is so more or less equal to potential energy is equal to, let us say, mgh, I guess, right, that is an analogy here, yes, but H would be similar to or analogous to what do we say now, the electric potential here, and constant here, and mass here would be with respect to charge. So, applying this with respect to our particular electron, let us say, how can we write this as bar is equal to charge for the electron will be equal to minus 1. So, F times here we have the potential, right, electric potential. So, from this, right, what do we have here? EH is equal to minus G bar by F, right, and again looking at the relevant equation that we have here, how can we write this as? That is going to be equal to plus 2.303 RT by F into PE, right. So, here from this particular setup, right, we now have what do we say, let us say if we have a particular value, let us say PE, we can calculate the redox potential, let us say, or the EH values, right, or we can calculate the molar Gibbs energies of these particular electrons, let us say, in that system, right. So, again keep in mind that here we looked at the relevant aspects with respect to the energy, right, say, right, And the take home message here would be that when you look at or try to understand the system, you see to it that the system would always move in such a direction as to decrease the energy of the system, right. So again, in the same case here, let's say we looked at a relevant aspect here as in with respect to the molar electrical energy, right, and looked at that approach to be able to calculate your redox potential in terms of the PE values or the molar Gibbs energy of the electron. Anyway, you do not need to mug up these little derivations that we have looked at, or minor derivations we have looked at, pardon me, but keep the background in mind. So now I guess we are going to obviously try to link what we have been up to. So here we are going to look at two half reactions, right. So here we have two half reactions, SO4 2- being reduced to H2S, right, and also HOCl, right, being reduced to Cl minus. And here we also have the log K and the P naught values for these relevant half reactions here, right. Again, what do we have here? We have the relevant half reactions here. Obviously, the standard form is to write them as reduction. For ease of understanding, we have written them as one electron transfer, both of them we have written them as one electron transfer, right. So again, here it is HOCl, what do we say, being reduced to Cl minus. You can obviously look at the relevant redox, not redox, pardon me, oxidation states, right. So here let us say we are going to first understand the system in terms of what we have discussed thus far, as in try to understand it in terms of the P naught values that we have looked at, right, which we have here, and we are going to understand this graphically, and it should hopefully help understand the system or visualize the system in a better manner. And at the same time, we are also going to look at the molar Gibbs energy of the particular electron and the redox potential here, let us say. So let us say I guess I have a graph here, right. So I have a graph here, and here we have HOCl and Cl minus in their standard states. So these would correspond to the P naught values obviously, right, and here we have for HOCl and Cl minus, right, here it is higher P naught value 25.1, and for the other half reaction it was 5.08. So for the redox couple HOCl and Cl minus, the P naught value 25.1 is higher than the P naught 2 value, let us say, right, 5.08 for the redox couple SO4 2- and H2S. So at the standard state, the molar Gibbs energy of this particular electron, let us say, in equilibrium with the redox couple HOCl and Cl minus would be at a lower energy state, right, compared to the electron in equilibrium with the redox couple between SO4 2- and H2S, right. So what does that tell you now? In which direction, let us say, would the reaction proceed, let us say, if it were at standard conditions now, let us say. Standard conditions again as in temperature, 25 degrees centigrade, pressure, and the activities being equal to 1, right. In what direction would it proceed now? Again, keep in mind that in a way that the energy would decrease, right. So as in the electron transfer would take place from this couple to the other couple, right. The energy is higher here, it would want to travel from the higher energy state towards the lower energy state, right. So let us try to understand this system in terms of what we have discussed earlier in terms of the PE now. So if you remember, when we looked at or analyzed the system in terms of PE, we said that if PE of 1 is greater than PE of 2, right, what did we have, or what did we understand about that now? We mentioned that one would proceed as reduction, right, reduction, and the other one would proceed as oxidation. So let us just try to visualize that here. What would that mean? That would mean here that HOCl will be reduced to Cl minus, right, and how will it be reduced by H2S, right, by H2S, right. So here what have you written now? 1 is written as reduction, right, this is reduction here. I mean, I am obviously not writing down the balanced half reaction here, and 2 will go through as oxidation. So what is happening here, if you look at the combined system here, H2S will end up reducing HOCl to Cl minus. And again, you know, two aspects to understand here. One was that P1 naught, right, is greater than P2 naught, and in that case we understood, or we looked at the relevant derivations too, I believe, right, especially with respect to P1 anyway, that 1 would go through as reduction, 2 as oxidation. And again, now here we can understand it in terms of the molar Gibbs energy of the electron, and that it would travel from, let us say, higher energy state to the lower energy state, right. But obviously this is at the standard state, right. Let us look at what it would be, let us say, if it is at non-standard state. So for that condition, let us say we are going to consider pH to be at 7, and I believe the example we are going to look at is going to be HOCl to be at 10 power minus 4 activity, and Cl minus to be at 10 power minus 3, and SO4 2 minus and H2S both to be at 10 power minus 3, right. And how can we calculate the PE values now, PE1 and PE2, right. So obviously, as we know, the general half reaction is PE1 equal to PE1 naught minus 1 by n being the number of electrons being transferred, times log Q dash, right, and Q dash is nothing but activity of the compounds in the reduced form, right, by the oxidized, right. So in this particular half reaction, what would it be? I guess the PE value would be equal to, right, PE naught would be equal to 5.08 minus 1 by n, only one electron transfer, right, 1 log Q dash, right. So what would that be here? So H2S power of 1 by 8 by SO4 2 minus raised to the power of 1 by 8, and obviously because we have H plus here too, we need to consider that H plus to the power of 5 by 4, let us say, right. And in this particular case, it would be PE is equal to PE naught is 25.1, right, minus log Q dash 1 by n, again the number of electrons being transferred is 1, so it is going to be 1 times the reduced form, right, Cl minus to the power of half, activity of water is 1, and divided by HOCl raised to the power of its stoichiometric coefficient half, and again H plus raised to the power of its stoichiometric coefficient half, right. So from here we can calculate the PE values, right, and let us see what the system would be. So here I have the calculated PE values for these two redox couples, as in HOCl and Cl minus, SO4 2 minus and H2S, and at pH 7 and 10 power minus 4 and 10 power minus 3 respectively concentrations for HOCl and Cl minus, and pH 7 and 10 power minus 3 for both these couples here, not both these couples, pardon me, for the couple of SO4 2 minus and H2S. So here we have the PE values, not the PE naught values. So here we have 21.1, and once we have the PE value, you know that you can calculate the molar Gibbs energy of the electron, right, and again how you can relate that to the redox potential. And same case here, we can calculate, or we are able to calculate the PE value, molar Gibbs energy, and again the redox potential, right. So let us try to understand this in terms of what we had earlier, let us say as in the standard conditions, right. So let us look at the standard conditions. So these were the standard conditions, right, and these were at the non-standard conditions of pH 7 and 10 power minus 3 and 10 power minus 4 concentration. Say again standard conditions to non-standard conditions, right. Again from here and looking at, let us say, the PE values or such, you can understand in which direction the or which particular, what do we say, compound or the reduced form would predominate or oxidized form would predominate, right, in relation to PE minus PE naught, right. So in one of the earlier classes, right, we looked at how, let us say, similar to pH and pKa, by comparing the PE values with respect to PE naught, we could understand, let us say, which particular compound would predominate. Let us just try to also throw a stone at that particular aspect here. So if I am looking at this particular what do we say couple, HOCl and Cl minus, so PE here is 21.1 and PE naught is 25.1, right. So similar to that pH and pKa graph, right. So what would it be like? Obviously there is H plus involved here too, so that is going to be slightly erroneous in trying to understand that here, but that is fine here. So if PE naught is 25.1, right, and PE is to the left of it or less than PE naught 21.1, so which form would predominate now, right, the one with the similar to the acid base, right, the one with the proton, or here the one with the electron, or the reduced form would predominate, right. So thus in this case, in this non-standard condition, the reduced form or Cl minus would predominate, right. So same case here again with respect to the non-standard conditions. In the non-standard condition for SO4 2 minus and H2S, right, what do we see here? Did we tabulate that right? 25.1, 21, yes. So again here too we see that PE is less than PE naught, right? So again from the similar approach of what we had earlier, we will understand that at the non-standard conditions, which one would predominate now? The reduced form or H2S would predominate, right? Again, that's just for understanding the system though. And going back to where we were, we are now trying to see in which direction, let's say, would the reaction take place now at the non-standard conditions, right? So earlier we looked at the standard conditions, but rarely do we see or come across such standard conditions. So at the non-standard conditions, the P values, the molar Gibbs energy, EH values and so on are the redox potentials, and we again have the relevant what do we say values of the activities and the pH values, right? So similar to what we looked at with respect to our standard conditions, right? We will first analyze it with respect to the PE. So here again PE1, right? Let's say I'll call this PE1 and this PE2. So PE1 is now still greater than PE2, right? So again what does that mean? That means that the first half reaction will go through as reduction, right? As in HOCl will be reduced to Cl minus, and how will this reduction take place now, right? And that will be taking place because H2S will be oxidized, oxidation. The second reaction, half reaction, will go through as half reaction, or H2S will be oxidized to SO4 2 minus. In the process, this H2S will release electrons which will be accepted by HOCl and then be reduced to Cl minus, right? So that is from the PE1 or PE2 approach here, right? So but let's say let's try to understand the system with respect to the molar Gibbs energy of the electron here. And here again you see that in the redox couple, right, the electron that would be in equilibrium with the redox couple SO4 2 minus and H2S, it's at a higher energy state, right? And you see that with the electron that's in equilibrium with HOCl and Cl minus, it's at a lower energy state. So again the electron would want to transfer from this couple to the, again this is a layman's understanding I guess, but more or less here you can understand the analogy with respect to the energy and the system wanting to move in such a direction that the energy decreases, right? So from higher energy to lower energy state, and that's what you see here. So the electron transfer takes place from this redox couple to this couple. So that means this couple is going to proceed in oxidation, or H2S is going to be oxidized to SO4 2 minus in the process, releasing the electrons which would reduce your particular HOCl here, right? So here I guess obviously now we should be able to understand the relevant aspects in terms of both the PE values, the molar Gibbs energy of the system, right? And you know, if not immediately I guess now have the intuition to be able to understand what would happen in the system, right? So now again in this context again you can look at the redox potential too, right, as in rel2 to the other. So these aspects we are going to start discussing in the next session, right, as in the electrochemical approach, let's say, and how or what do we need to understand when we look at a cell, what's an anode, what's a cathode, what takes place at that, and why is that relevant to us, and so on, right? And I guess with that I'll end today's session, and thank you.